Dear students, welcome to theory session number 11 on the chapter of chemical bonding in physical chemistry. In our last theory session, we did our discussion on the different types of molecular orbital configuration of different molecules like lithium, beryllium, boron, carbon, nitrogen, oxygen and fluorine. Now, in today's theory session, we shall be discussing about the formation of molecular orbitals that takes place in heteronuclear diatomic species or AB type of molecules. So our topic of discussion is formation of molecular orbitals in a heteronuclear diatomic species. So what is heteronuclear diatomic species? The molecules of AB type are known as the heteronuclear diatomic species. The AA type of molecules, for example oxygen, nitrogen, etc., these are all known as the homonuclear diatomic species. So hereby we shall now see how the molecular orbitals are formed in the heteronuclear diatomic species of AB type of molecules. Examples of this AB type of molecule will be CO, CN, CN minus, NO, NO minus, etc. So these are all examples of heteronuclear diatomic species. In heteronuclear diatomic species that we will be studying today, there are a few points that we need to cover. The first point is that A and B atoms belong to the second period of the periodic table. And number second point is the electronegativity of A is less than that of B. So these two are very important points. One, that the A and the B atoms of this heteronuclear diatomic species belong to the second period of the periodic table, and also the electronegativity of A will always be less than that of B. Let us compare these particular molecules. If you have CN, we can say that nitrogen is more electronegative than carbon. Also, if you have NO, we can say oxygen is more electronegative than nitrogen. So wherever may be the combination, whether this is a CN or NO or NO plus or NO minus, always the electronegativity of the atom B is greater than that of the atom A. Now since both of those atoms belong to the second period, we can say that each of them has 2s, 2px, 2py and 2pz orbitals. So since both of the atoms constituting the molecules, the heteroatomic molecules like CN, NO, etc., they belong to the second period, we can say that each of the atom contains the above molecules as such: 2s, 2px, 2py and 2pz. So we can say there are 4 atomic orbitals in its valence shell. So we can represent the atomic orbitals of A by 2sa, 2pxa, 2pya and 2pza. So I am representing the atomic orbitals of A as such. So there are 4 atomic orbitals in the valence shell of A. Similarly, we can represent the 4 atomic orbitals of valence shell of B as such: 2sb, 2pxb, 2pyb and 2pzb. So now the overlap will take place between the 4 orbitals of the atom A and with the corresponding 4 orbitals of the atom B, and this will give rise to 8 molecular orbitals. So overlap of 4 orbitals from A and the overlap of 4 orbitals from B will give rise to 8 molecular orbitals, and we can represent the molecular orbitals as such. We can represent it by sigma 2s bonding, sigma 2s antibonding, pi y bonding, pi z bonding, sigma x bonding, sigma x antibonding, pi y antibonding, this sigma x bonding won't be here. So then we'll have a pi z antibonding, and lastly we will have sigma x antibonding. So there are formation of 8 molecular orbitals. I am not mentioning here the 1s level because 1s level is the lowermost orbital and which never takes part in bonding. If we represent the 1s orbital level, I can write the orbitals as such, that 1s of A, then 2s of A, 2px A, 2pya and 2pz A. Similarly, for the atom B, we can write 1s of B, 2s of B, 2px B, 2py B and 2pz B. And then the overlap will give rise to such orbitals. First we'll have sigma 1s, then we'll have sigma star 1s, then sigma 2s, then sigma star 2s, then we will have pi y equal to pi z, then we'll have sigma x bonding, then we'll have pi y antibonding equal to pi z antibonding, and lastly we will have sigma x antibonding orbital. So this is the level that is formed if two particular atoms or heteroatoms of type A and B, which belongs to the second period of the periodic table, and where electronegativity of A is less than that of the B, they overlap among each other and will give rise to this 10 molecular orbitals. Now, in the formation of these molecular orbital, one more important thing is that we have assumed the x-axis to be the molecular axis. So in this case, the x-axis is the molecular axis. Now the relative order of these molecular orbitals have been depicted as per the order that is given above. We can say that since B has a greater electronegativity than A, the atomic orbitals of atom B have lower energy than the corresponding atomic orbitals of atom A. This particular point should be kept in mind while we will be drawing the diagrams of the molecular orbitals of molecules such as carbon monoxide or CO, nitrogen oxide NO, cyano molecules, that is CN, etc. Now we first draw the molecular orbital configuration for a CO molecule. So first topic is the molecular orbital configuration of a CO molecule. First thing, we can say that the CO molecule is a heteronuclear diatomic molecule of AB type. This we have already discussed, and these atoms, visually the carbon and the oxygen atom, have 4 and 6 electrons in their valence shell respectively. How? If we have the electronic configuration of carbon, we can see it is 1s2, 2s2, 2p2. So we can say in the valence shell, carbon has 4 electrons and a total of 6 electrons. If we are representing oxygen, we can say that it is 1s2, 2s2, 2p4. So it has 6 electrons in the valence shell, and in total there are 8 electrons. So total in a carbon monoxide molecule there are 14 electrons to be distributed in various molecular orbitals. So now we have to write down the MO configuration for a carbon monoxide molecule.